We are now on YouTube, I think.
Yeah.
So 1 minute left. I will share the screen and we can start if you want.
I think we can start. What do you think, Ignacio?
Well, we are only 4 people in here.
I don't know if on YouTube some more attendees, but
We can start if you want.
yeah.
Yeah, I think we can start.
Okay. So, hello everyone, and welcome to the 9th section of the ISRM Young Member Seminar Series. My name is Federico Vagnon from Politecnico of Torino, and Dr. Ignacio Perez from University of Vigo, Spain, and I, as a part of the ISRM Young Members Group, are happy to chair this 9-monthly seminar. It's a great pleasure for us to be here today, and we would like to thank you for attending this 9th session. Before starting, we would like to thank the support from the International Society of Rock Mechanics, and especially to Sevda Del Doca, ISRM Vice President for Australasia and Chair of the ISRM Young Member Committee. We also would like to thank to all young member representatives of national groups that have joined this initiative from Spain, Australia, New Zealand, Japan, China, Chile, Canada, and among others. Finally, we would like to thank Dr. Alessandro Valletta and Dr. Anuradha Khetwal for agreeing to present their work in this session. Before our speakers begin, we would like to take a moment to present the key information about the seminar series. This project attempts to promote young community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and the academia, and to strengthen relations between different countries. We would like to invite you. We would like to invite a variety of young members to participate to this seminar series. And the criteria for the speaker are as follows: be an ISRM member, have a maximum age of 35 years or 40 years if a PhD degree was obtained in the previous 5 years, have worked in rock mechanics and rock engineering for a period no longer than 10 years. Speaker nomination can be made by the nominee's national group or by some other person or organization acquainted with the nominee's works. Self-nomination are also accepted. Nominations are to be addressed to the ISRM Young Member Seminar Series organizing committee. On the screen, you can see our contact email. This webinar will be held every month, and we invite you to keep in touch. So we will now begin the first seminar of the day. I remember to the speaker that each presentation will last 20 minutes and will be followed by 10 minutes of Q&A. And for the smooth running of the seminar, please turn off your camera and microphone during the presentation. And if you have any question, you can use the chat and also raise the hand feature. Okay, so let's move on. And let me introduce the first speaker of today's talk. That is Alessandro Valletta, who is a postdoctoral research fellow at the University of Parma, Italy. And after obtaining his master's degree in environmental engineering at the Polytechnic University of Milan, he attended a postgraduate second-level master course focused on the analysis and mitigation of hydrogeological risk held by the CERI Research Center of the Sapienza University in Rome. He obtained his PhD in 2022 from the University of Parma with a thesis focused on the automatic identification of landslide events for risk management and early warning procedures. His research includes the application of automatic instrumentation for geotechnical monitoring activities and the development of data elaboration algorithms for early warning system. Today, he will present in a talk entitled Deformation Analysis and Monitoring in Underground Construction, Automatic System to measure convergence and preconvergence effects. So, Alessandro, the floor is yours.
Okay, thank you very much. I am starting my presentation in a second. Here we go. So you can see my slides correctly?
Yeah,
Yes,
perfectly.
perfectly.
Okay. So good morning or good afternoon, everyone. As Federico said in the introduction, my presentation is mainly with the automatic system that can be used to measure convergence and preconvergence effects in underground constructions. The importance of this topic relates mainly to the extreme complexity that characterizes this type of works, so underground construction, which requires a careful planning and design in order to be conducted correctly. And in this context, it is very important to have an appropriate monitoring activity in order to reduce the risk connected to the design and the advance of the project. In fact, in the realization of underground construction, we can see different types of problems related to the general environment, such as the high stresses and high water pressure that involves the realization of the tunnel, but also other parameters related to the high humidity and the dust that is generated by the works. So we can focus on different parameters depending on what we are interested to monitor, such as the deformation of the tunnel cavity and the tunnel face, the subsidence and the presence of local displacements in the tunnel cavity, and other effects that the excavation works have on the surrounding rock mass. Among these parameters, the ground deformation is probably the main parameter that we have to take into consideration if you want to understand the rock mass response to the excavation process. And generally, we can distinguish three different components of the ground deformation, which are summarized in this image. The first one is the extrusion of the tunnel face, which is the primary deformation response of the tunnel, and it depends on the rock mass mechanical behavior. We have the convergence of the tunnel cavity, which corresponds to the decrease of the theoretical cross-section of the excavated portion behind the tunnel face. And lastly, the preconvergence of the cavity, which interests the tunnel profile ahead of the excavated phase. So taking into consideration these three components, we are focusing in this presentation on the convergence and preconvergence effects. Over the years, different monitoring methodologies have been developed to measure these effects. And for what concerns tunnel convergence, target-based measurements are among the most used in this context. And this type of monitoring approach relies on different targets located along a cross-section of the tunnel, and the displacement of the section is measured by monitoring the displacement of these targets with the different approaches. We can use different devices such as the total station, a terrestrial laser scanner, or we can rely on optical sensor for a photogrammetric approach to the measurement. We have also these other types of monitoring approaches, which are based on the installation of several distometer nails around the cavity, and the objective is quite similar to the target-based measurement that we have just seen, and they rely on the.
Sorry, Alessandro, we cannot see the screen because it's freezed. Sorry.
Okay.
For interrupting you. Can you check
if
I
can stop the share, the screen share, and can.
I thought it was a problem of mine, but it seems like
there was some
now it's correct. Sorry.
Right. So maybe it was a problem on my side. There was a warning on my screen, and okay. But if you say now it's
okay.
It should be okay.
Now it is okay.
Okay, perfect. Thank you. So as I was just saying, the tape distometer measurement approach is quite similar to the target base in the sense that we have a specific object placed on the tunnel section, and we measure the movement of these elements, in this case by measuring the distance between different distometer nails with a mechanical or a digital tape distometer. A different approach relies on sensor-based measurements, and in this case, the tunnel convergence is detected with the sensors able to identify tip variation of the tunnel section, which can give us a measure of the movement of the entire tunnel section. This sensor can be wireless or wired, depending on the application. And all these approaches are quite well documented in scientific literature. We cannot say the same for the preconvergence. Sorry. Okay. For the preconvergence approaches, where the methodologies are much less used, or at least less documented, I should say. We have some approaches that relies on the use of multi-base extensometers installed vertically above the tunnel cavity. So this is an approach that can be exploited only if the overburden is quite shallow, for obvious reasons. Otherwise, we are not able to reach the tunnel cavity from the surface. Other approaches relies on the installation of in-place horizontal inclinometers in a borehole located on the tunnel crown, and both these measurements are direct. So we are measuring the actual preconvergence of the tunnel cavity, so ahead of the tunnel face. There are also some methodologies that relies on an indirect measurement of this phenomenon, which are based on the measure of the extrusion of the tunnel front, and by measuring the amount of deformation that the tunnel face is experiencing, we can derive the preconvergence of the cavity by using empirical formulations and empirical graphs, as the one I showed in this slide. Obviously, all these devices, all these instrumentation should be selected depending on the case study we are working on. So in each phase of the monitoring activity, we should always take into consideration what is the most appropriate device that we have to use. And in addition to that, we should also take into consideration what's the best approach to the data acquisition process. Generally, we can rely on two different approaches, which is the first one, the manual approach, where instrumentation is read by an operator. These are usually quite easy to use, and they have a long battery life in the sense that the power supply is quite easy to provide. But on the other hand, they can achieve only low sampling frequency. On the other hand, automatic approaches relies on autonomous reading of the instrumentation and can be managed by remote, so without the need of an operator on site. And they can give us the possibility to reach higher sampling frequencies. And I'm focusing on this second group of devices to introduce two type of instrumentation based on a technology named Modular Underground Monitoring System, which was developed after several years of research in the field of geotechnical monitoring by a private company originally born as a spin-off of the University of Parma called ISRM. The MAMS devices are composed of different nodes, epoxy resin nodes named links, which are connected to form a long chain of an arbitrarily long chain of sensor, which can be customized according to the monitoring needs. And in this presentation, we are going to focus on two main devices developed specifically for underground excavation application, which are the shear array and preconvergence array. Both these devices relies on the same monitoring system structure, which takes advantage of IoT-based technology to improve the automatic system performances and can give us a series of advantages, as we saw in the previous slides. So we are able to adjust the sampling frequency depending on the monitoring phase we are working on. The data can be collected without the need of an operator, so we remove a degree of uncertainty in the data acquisition process. We can identify a series of cause-effect correlations thanks to the high amount of data collected, and we can implement early warning procedures thanks to the near real-time approach that this methodology can give us in the monitoring activity. So the first device is the shear array, and it's a monitoring instrumentation that was developed for the assessment of the convergence phenomena and localized deformation in a specific tunnel. So the composition of the instrumentation is basically an array of resin nodes, as I said before, and each one of these node or link, as it's called in the MUMS context in the MUMS philosophy in devices, is equipped with a 3D MEMS sensor, which can give us the tilt and as a consequence, the displacement of the specific point on which is installed. Links are connected with the fiberglass rods to guarantee the alignment of the sensor and the distance of the sensor. And each link is connected with a quadruple electrical cable that connects all the sensor of the array. To better adapt to the inverted arch, the Kevlar, a Kevlar cable can be used instead of the fiberglass rod for a better fitting of the tunnel section. The shear array was tested before its application in a series of laboratory tests that involved the comparison of the data provided by the 3D MEMS sensor with topographic and photogrammetric measurements, and the results were quite positive, and the results of the monitoring activity given by the shear array was in accordance with what the photogrammetric and topographic measurements were displaying during the different tests, which involved multiple deformation of the section in several points of the array and a single deformation at the top of the section, with the deformation ranging from several millimeters to some centimeters. The pre-conver ray is the other device I am going to present in my speech, and is designed mainly for the near real time of preconvergence deformation during the tunnel excavation. And since it's installed on the top of the section in advance with respect to the tunnel face, it can also provide deformations ahead of the tunnel face, but also behind the tunnel face, depending on the tunnel face position during the excavation process. The structure is quite similar to the shear array, so we have an array of nodes. In this case, also equipping a 3D MEMS sensor, and the device is designed to be installed and cemented inside an advancing borehole or inserted inside one of the 4-pore reinforcements. And the instrumentation can be placed in horizontal or tilted configurations, depending on the context of the scenario. Similarly to shear array, the pre-conver array was tested in laboratory with a series of deformations imposed on a prototype of the pre-conver array. You can see on the right the results that we obtained during this test, where different deformations were imposed on different parts of the device, and comparison with the topographic data were provided, and also in this case the results were quite consistent during the different tests, and the device was able to represent correctly the deformation of the instrumentation. The data I just want to mention the data visualization part of these devices, because it's quite frequent with the high sampling frequency to have a considerable amount of data and information related to the monitored element that should be managed appropriately for right visualization, browsing, and to extract meaningful information from this data. So for the instrumentation, we developed a web-based visualization platform that gives us the possibility with different graphs and tools to browse all the information in real time and check how the monitoring activity is progressing. To give a practical example of the application of these devices, I'm showing the results from the monitoring activity of a shallow tunnel realized in the Principality of Monaco, where one pre-conver array and 3 shear array were installed to monitor the influence of the excavation work on the surrounding environment and the interaction between the structure and the rock mass. The pre-conver array was composed by 15 pre-conv links, so a total length of 15 meters. The sampling frequency was set to 10 minutes, so 6 readings for each hour. And it was installed on the top of the tunnel entrance in a PVC casing. In this case, we also had a topographic target near the installation point of the pre-conver array, and this target gave us the possibility to evaluate the absolute displacement of the device during the monitoring activity. So as you can see from this image, we managed to evaluate the deformation of the tunnel crown height of the excavation phase during different phases. So in this case, we have the deformation when the excavation works reached a bit more than 2 meters from the tunnel entrance, and the evolution of the deformation in the tunnel crown was followed by acquiring different deformations during the progressing of the excavation works. As you can see, when we reached the end of the instrumentation, so after 15 meters, sorry, from the tunnel entrance, this was the displacement that the device was able to measure, and the evolution of the deformation during the excavation works. For what concerned the shear arrays, as I mentioned before, we had 3 different arrays in the tunnel, and the first one, the array DT107, was installed in a section with 22 links, so 22 let's say calculation points of the device, while the other 2 arrays, 108 and 109, were composed by 16 links. And in this case, the sampling frequency was set to 1 hour. The CRRA gives us the possibility to visualize the results in a similar way if we take as a reference the distometer nails we saw before, basically a convergence star where we can define a single segment connecting different points of our section. And by evaluating their variation over time, we can gain information related to the convergence of the monitored section. So you can see for the section here reported, which is referred to CRRA 107, the evolution of the different segments over time. And using the same principle, we can also evaluate the variation of the section area over time, and also the deformed section profile as the monitoring progresses. Moreover, we can focus on a single sensor of the array in order to evaluate specific deformation in a certain part of the section. As an example, I reported here the deformation of specific links in CRRA 107 and 108 close to the tunnel crown, and we can see how as the monitoring progresses, we can observe the convergence of the tunnel crown reaching up to 8 millimeters at the end of the monitoring activity. So to conclude my presentation, we saw that the complexity that characterizes the execution of this construction is particularly high, so appropriate monitoring activity of the tunnel cavity focused on the deformations effect that are affecting the excavation works is fundamental to reduce the risk connected to the execution of the tunnel excavation and to control the interaction of the structure with the surrounding environment. I presented the different approaches to achieve this task, including 2 devices featuring an automatic acquisition, elaboration, and visualization process, the preconv array for the identification of preconvergence effects, and the CIR array to assess the convergence in different parts of the tunnel cavity. And this approach, or in general, the automatic monitoring approach to this applied to this kind of structure can give us a comprehensive description of the deformation that are generated by the underground work on the surrounding environment. So thank you very much for your attention.
So thank you very much, Alessandro, for your very clear and interesting presentation. Now I think that we have more or less 10 minutes for the Q&A session. Are there any questions? I have a question, Alessandro. Which is the sensibility or the precision of both the preconv and the CIR array?
So I can show the laboratory test we carried on the instrumentation, and in this table is referred to the single deformation at the top of the section. And we can see the evolution of the deformation from 0 to 15 millimeters. And this is the difference between the measurement recorded with the topographic device and the variation recorded by the shear array device. And the difference varies from 0 to 0.5 millimeters. In a real case scenario application, which is different from the one I presented here, but I remember a similar result. So something like 0.2 millimeters in terms of precision of measurements of the shear array. And the pre-conv array is more or less the same. I did not report here the exact numbers, but we are on the same
range. Okay.
Yeah, on the same range.
And the preconverge is cemented in the borehole.
Yes, it is cemented.
So you can use both for coherent or incoherent material.
Yeah, it just needs
mainly rock or in I don't know, in civil, in urbanized area in which you have deposits or something like that.
Yeah, basically it just needs a borehole to be installed within, and in that borehole the instrument is cemented. So if the monitoring, not the monitoring, but the general context of the excavation works allowed the installation of a borehole in the advanced core, the instrument can be installed and cemented in that borehole without any problem.
Okay, thank you very much also for the reply to this question. Are there any other question?
I have a question. Well, first of all, congratulations for the presentation and for the for the work behind your presentation. Very interesting. And well, I have a question regarding the use of the sensors. Are you applying or thinking in applying low-cost sensors like those available for Raspberry Pi or Arduino, these low-cost technologies? Does it make any sense, or what are the possibilities of these sensors?
To be applied in this specific field, right? So because the MUMS devices, so I can taking as a reference this device, the link basically was developed originally for landslide monitoring. So it was basically an automatic inclinometer, and both shear array and preconv array are an evolution of that device. So in order to keep every device as much similar as possible, in order to have an optimized elaboration, visualization, and so on, we decided to use the same sensor. I don't know if low-cost sensor, at least based on Raspberry or Arduino or something similar, is viable mainly due to the installation conditions. So if we have to basically create a single node, a single link, because the node is not particularly big. Is if I remember correctly, less than 20 centimeters in terms of length, and the diameter is only some centimeter in order to fit in the borehole. It's quite difficult, at least for what we studied in the past years, to fit something like that in a link or a structure like that. So we tried to use those devices because they are indeed quite useful in application where the installation is not so strict. Can I say, like in we used it in monitoring devices for debris flow barrier or rockfall barrier, where we have a easier installation in terms of space available for the device. So yeah, we did not study in depth the use of such devices, but my idea is that the installation context can be a bit of an obstacle for the application of this type of sensor.
Okay, thanks. Thanks for your reply. And well, regarding, I have another question, just a curiosity regarding the high amount of data I imagine you can collect from these systems. Have you planned or are you carrying out some studies on the analysis of this such amount of data by means of any machine learning algorithms, or well, trying to reinterpret some empirical relationships or methods? Because I guess you have lots of data from these collected from these devices.
Yes, so I did not talk about the data elaboration part because yeah, it was another topic that would have needed a lot of time to explore. But within the structure of the MUMS monitoring system, there is this part. I hope you can see the cursor on the screen. That basically is the conversion of the raw data that the device are providing into actual results, so physical quantities. And within this data elaboration process, there are a lot of statistical analysis in order to identify, for example, some outliers, or to define specific trends that can be extracted from the data elaboration process. And we are including different algorithms in this software in order to have the most meaningful results from the data that the devices are providing us. And for what concerns machine learning, we are working on that once again on landslides monitoring, mainly because we have a larger amount of data. We have more experience and more information from different sites that relates to landslides. So it's a research that we are carrying on we have started recently working on that side of data elaboration, but it's showing I would say promising results. So I think that something based on machine learning or artificial intelligence will be for sure integrated in the elaboration process.
Okay, so many thanks for
thank you very much.
Your answers. Well, I don't know if we have more questions. If not, we can proceed with the next speaker. Thank you very much, Alessandro, for your interesting presentation and
thank you.
All the works behind what you have shown us today. Well, the next speaker will be Dr. Anuradha Khetwal from WSP in USA. Well, I will give a short presentation of her CV. Dr. Anuradha Khetwal is a geotechnical engineer at the already mentioned company in USA, WSP. Previously, she was employed for almost 6 years as a tunnel engineer with a subsidiary of Lombardi Engineering Limited in India. She was involved in the design of various tunneling projects in the Himalayas, Beirut, Switzerland, and other parts of the world. She did her PhD at the Colorado School of Mines in the USA, and the topic of her research was the implementation of discrete event simulation approach for the prediction of TBM performances for a direct implementation in the industry. And today, she will be giving a talk with the title shown on the screen, Introducing CSM 2020 Discrete Event Simulation Model for Predicting TBM Utilization. So the floor is yours, Dr. Khetwal. You can proceed with your presentation. Thanks.
Hello, everyone. So firstly, thank you, ISRM young member, for this seminar. Today, I'll be talking about the CSM 2020 Discrete Event Simulation Model for Predicting TBM Utilization, which is my PhD research. The outline of this presentation is as shown here. Firstly, I'll introduce the concept of machine utilization and gaps in the existing research. Then I'll be defining the scope, and then we'll walk through the discrete event simulation modeling, the adopted methodology, the data collection system for setting the input, and finally, we'll conclude with some sensitivity analysis and its results. The main question is how one can estimate whether the machine is working or is used efficiently. The success of any project using tunnel boring machine is measured by calculating the advance rate, which is the total distance the machine has traveled in a particular day. Advance rate is the product of rate of penetration and machine utilization. Rate of penetration is the rate at which machine penetrates the ground, while utilization is defined as the percentage of time the machine is boring per total time. The average utilization is around 30 to 35%, which means only 35% of the time the TBM is boring and rest of the time the machine is in the idle condition. As shown in the formula below, the utilization is the percentage of ratio of boring time TB and total time, which is the sum of boring time, ground-related delays, maintenance-related delays, time taken to extend utilities, transportation-related delays, and other unforeseen activity times. To better understand the significance of this utilization estimation, let us consider a project. The project takes 1 year or 365 days to excavate a 5-kilometer long tunnel with an average penetration rate of, say, 3 meters per hour. The average rate comes to be around 13 to 14 meters per day, with the utilization of around 19%. Now, for the same project, if the utilization is 30%, then the advance rate will be around 21 to 22 meter per day, and the completion time will reduce to 231 days. So we can see that there is a reduction of 134 days, and therefore there is a significant reduction in the total cost of the project and overall completion time. Currently, this utilization number is based on the experience of the designer estimating the completion time. Therefore, a method needs to be established to have a more reliable approach for machine utilization. The scope of this research is to develop a platform for utilization estimation of TBM using discrete event simulation approach. Discrete event simulation, or DES, is defined as the simulation approach in which events are considered as discrete and they are interconnected at particular sequence that are representative to the system. In our case is the TBM. The time allocated to these events are given as time distributions that are combined together using Monte Carlo simulation to get the desired output. The simulation has a capability to encompass the uncertainties involved in the input parameters by increasing the number of replications. And therefore, in this research, discrete event simulation was used as a platform for developing this machine utilization estimation model. The flowchart of CSM 2020 is shown here. It was prepared to encompass the tunneling activities that are shown. The frequency of occurrence of these activities were determined by counting their occurrences along the tunnel length. The randomness in performing these activities were considered by preparing the time distributions of each activity. This flowchart is based on 2 levels, as you can see. The first is where the model checks the shift and allocate time for meeting that happens at the start of every shift. Then in a shift, there are many cycles or strokes that are performed as shown in the flowchart below, as shown in the flowchart later. The boxes with the same color shows that these are part of one activity. So to understand the CSM 2020 model, first, the components of the TBM need to be understood. And we need to understand these components. So this slide shows various components of TBM and the project site that directly or indirectly affect the machine utilization values. The activities that are performed at the cutter head are cutter inspection and change, ground support installations, probe drilling, and segment installations as per the site requirements. Activities like electrical, mechanical, and hydraulic breakdowns and repair, maintenance, loading of mug, surveying are performed at the backup area. Installation of California switches and utilities extension happen as the tunnel length progresses. At or near the portal, activities like mug disposal, loading and unloading of supplies take place as shown in the figures here. These all affect the utilization of the machine as the excavation process are related to their completion. When it comes to utility extension in CSM 2020, the 3 utility extensions were considered. These are the ventilation, power cable, and water pipe extension or drainage. The ventilation was extended every 200 meters, while power cable was extended every 100 meters. The water pipe was extended every 50 meters and is fed into the simulation model. The transportation system related delays, the check regarding the muck conveyance system is given as was shown in the flowchart. A total of 3 trains and 3 California switches was considered. It can, however, be changed as per the site requirement or the length of the tunnel. The California switches were placed at 1,000 meters, 3,000 and 7,000 meters for this particular simulation model. The delays related to transportation systems include the track replacement, conveyor belt repair, weight of train at California switch, derailment, and time taken for loading and unloading of supplies. The ground-related delays include delays or activities include the support measure installations, cutter change, probe drilling as shown in the figures here. These were all included in the CSM 2020 simulation model. Provision of choosing the probe drilling throughout the tunnel length is given and is not a random activity in the CSM 2020 model. So when we assign the tunnel activities, we need to understand the sources from which we can get this data. The sources from which these data is shown here. The TBM related information, for example, can be obtained from specification report and sensors that are attached at the cutter head. These data include RPM, thrust, number of motor, torques, etc. The ground-related information can be obtained from GBRs or geotechnical baseline reports, while other project information can be obtained from alignment report, historical data, and other similar project data. The details regarding the activities can be obtained from operator sheet, shift reports, manually recording the time, and interviewing the personnel performing that activity. And this is how the data was collected for the CSM 2020 model. This flowchart shows the methodology adopted to get the data. So firstly, site visits were conducted to understand the tunneling process, and the pictures were shown from these site visits. The data from the 9 projects as shown here were compiled, and the time distribution of various time activities were prepared. It was set as an input in the CSM 2020 simulation model for utilization estimation. This table shows the details of the 6 projects that was considered from Dr. Nelson's thesis and was built in US, and the 2 projects that was built in Iran. The C11, C31, Culver Goodman and Chicago Top tunnels were built in somewhere in 1980s, while the Carriage and Nosud projects were from 2006 to 2012. These 6 projects from US were built using the gripper TBMs, while Carriage and Nosud were built using double shield machine. It can be seen that US tunnels these US tunnels had utilization values that ranged from 32 to 36%, while the carriage and Nosud had 19 and 24% of utilization values. This difference can be attributed to many factors like the ground conditions, the length of the tunnel, the type of TBM, etc. However, no clear identification can be made as the two sets had different geology and different TBMs and different tunnel lengths. The data set of these 9 projects listed before were analyzed, and the list of tunneling activities was prepared that directly or indirectly affect the machine utilization and is shown here. These activities were then analyzed against the boring process to determine whether these activities are performed in series or are in parallel. Let's say, for example, segment installation. If the project has a single shield machine, this particular activity will be considered in series to the boring or the excavation process. However, for a double shield machine, it can be considered as a parallel event. For the open TBM, where the segment installation is not the scope of the project, this activity can be annulled and is the main factor of the CSM 2020 simulation model. Based on the data that was available, it was divided as shown here to prepare a data collection template. For this, Visual Basic of Application or VBA was used. The 5 modules were prepared as shown here. These were the basic information, Tbm specification, geotechnical details, transportation details, and shift details. In basic information, project name, application, tunnel length and diameter, ground type, mucking type, and stroke length was defined. In TBM specification, type of TBM, its condition, whether it's new or it's refurbished, the specifications like the power, the number of motors, RPM, cutter size, and shield length and other backup system length was defined. In geotechnical details, the geotechnical units, their rock mass properties, the length of each geotechnical unit, their distance from the portal, and possible ground troubleshooting measures that need to be considered for that geotechnical unit can be assigned here. In transportation details, the transportation related activities like number of rails, trains, or California switches, and altogether whether a conveyor system is to be used can be defined here. In shift details, the number of shifts, the delay, the number of hours of shift, the number of routine maintenance that happen in any project is defined here. Finally, these all are combined and is compiled in a separate sheet using this individual geotechnical unit data sheet, which is read by the CSM 2020 model, and then the simulations are ran accordingly. For assessing the accuracy of this utilization estimation, a comparison was made as shown here. The NTNU model proposed in 1998 with further addition of tunnel length factor in 2016 was considered. The other models include the CSM model that is developed in that is based on the data that was available to them in 1991, the RME model proposed by Biniaski, and Farouk utilization model that was proposed in 2012. Graphical representation of the results for the 8 projects are shown here. The red dots corresponds to the utilization that was obtained from site, which is the actual data. And the pink rectangle represents the results from the CSM 2020 model. The results showed that using this simulation model, the difference of 7% was obtained, while NTNU 2016, as shown in the yellow triangle, overestimated the utilization by around 19%. The variability in the results can be attributed to many factors like unlike simulation or unlike CSM 2020, the other performance prediction models are based on empirical formulas that are derived using the data that was available to them and very limited flexibility in the formulas are given to account for the variation in the projects. The CSM 2020 approach had an upper hand in which most of the tunneling activities that are project specific can be accounted for in the analysis and can be customized. However, there are some assumptions also that were made in the input and that needed to be highlighted. For example, the DRI value, drilling rate, was obtained from the table from the Bruland thesis in 1998. And also the effect of curve was not considered as the alignment details was not available for all the projects that was considered in the analysis on comparison. This table shows the parameters that are considered in the simulation model. You can see that the ground related parameters were considered as in terms of ground support installation and not as a factor of rock mass properties. The data regarding the slope and the curves in the tunnel alignment was not available and therefore was not considered as a in the analysis for the CSM 2020 simulation model. This is an extension of the previous table. Here you can see that the machine specification was not part of the simulation as identification or quantitatively identifying its effect on utilization was not available based on the data of the 8 projects and the 9 projects. Further sensitivity analysis was performed. So the sensitivity of utilization towards change in geology and the number of trains was studied. The analysis was performed as this analysis was performed based on the carriage project. And you can see that it contributed around 13% of the total downtime. 5 cases were analyzed by changing the number of trains and the sequence of geotechnical units. As shown in this alignment drawings, it's a hypothetical drawing. The sequence of 5 geotechnical units were changed to assess the extent of variation in the utilization when poor ground condition are near the portal or is present later at a distance from the portal. In case 4, you can see that the units with RMR 35 and 21 appear at the start of the portal, while in case 5, they are present after 1200 meters from the portal. As can be seen from the table, the percentage of downtime due to change in the transportation system lowers with increasing the number of trains and the addition of California switches. Analyzing case 4 and 5, it was seen that even if the ground condition was good at the portal in case 5, the utilization was not very high. However, in case 4, where it appeared later along the alignment, significant increase in the utilization was achieved with variation of around 15%. Overall, utilization changed from 12.5 in case 12.6 in case 5 to 28% in case 4, showing that simulation model or the CSM 2020 model has the capability of showing sensitivity with the change in the sequence of geology. Further, 11 cases were studied, and as you can see from the tables here, the first 6 cases, for the first 6 cases, the time allocated to perform these activities as shown are varied plus minus 50%, and utilization was estimated accordingly. These were analyzed for carriage project, taking carriage project as the base. A total of 50 replications were performed for each case. The variation in utilization of the 6 cases are shown here. It can be seen that increasing the time to perform ground-related issues reduces the utilization. The maintenance showed maximum sensitivity with a variation of around 3%. Transportation delays showed around 2% variation. These 6 cases proved that maintenance, which contributed around 19% of the total downtime for the carriage project, is the critical factor, and optimizing this activity can help in increasing the performance of the machine significantly. Transportation delays is yet another factor whose optimization can enhance the utilization of the machine. Comparing case 7, 8, and 9, we can see that with the reduction in the frequency of occurrence of utility extensions, an increase in the utilization estimation, overall utilization is achieved. By this, if you are increasing the length of the utilities, for example, the ventilation duct from 200 meters to 250 meters or so, the utilization value will increase, and that is what the sensitivity analysis showed. Comparing case 10 and 9, it was seen that changing the rod length in probe drilling, the gain in 1% was achieved. However, the gain in utilization due to reduction in utility extension frequency is masked due to probe drilling, showing that probe drilling is more critical than the utility extension. With this, I conclude, and we can say that stochastic behavior of utilization can be obtained using this discrete event simulation method. The CSM 2020 simulation model is a platform that can be used to estimate utilization before construction as well, if you have the data available for any nearby or similar project. The data template is proposed where the input parameters for utilization estimation can be extracted. The choice of mug transportation system, whether it's a conveyor belt or train, can be made, which allows for the comparison too. Critical locations like change in geology, the effect of addition of train and California switches can be identified. And the bottlenecks in the tunneling process can be identified using the simulation model. The research is ongoing to extend this CSM 2020 model for the soft ground TBMs. So we can say that the three key issues that are addressed in the CSM 2020 model are: it can incorporate the uncertainties in the time allocations in various tunneling activities using Monte Carlo simulation and this discrete event simulation approach. The capability to estimate utilization as per project specific requirements by assigning particular time for tunneling activities that are specific to the project. And then quantitatively making an decision regarding the TBM selection and specific and its backup. And so an informed decision can be made. This is the paper for reference and is the primary reference for this presentation. Other sensitivity analysis and comparisons can be seen in these list of publications. At last, I would like to acknowledge Colorado School of Mines for giving me this opportunity to pursue this research. I would like to thank my advisor, Dr. Jamal Rustami and Dr. Priscilla Nelson for their guidance. I would like to thank Dr. Omid Frouk for sharing his data and for his continuous support. My family and friends for their unending encouragement. And finally, again, ISRM young member for this opportunity. With this, I conclude. Thank you for your attention. I'm open for questions now.
Well, thank you very much, Dr. Anuradha Khetwal, for your excellent presentation. Excellent work, and of course, the high amount of papers derived from your PhD in such good journals. So this is an example of the quality of your work, of course. So now we have some minutes for any questions, if any. I don't know if the audience, the little audience, has any question. Yes, we have a question from Johnny Villavicencio. Well, I'll read the question and then you ask. In cases like double shield TBM, where excavation and installation of the precast segments can be done simultaneously, it is expected more time of utilization, but results are quite lower. Any particular reason? This is the question from John.
Yeah.
Thanks for the question, of course.
So, yeah, I can understand from where this question is coming. Let me go back. It is from this slide, basically. So, As you can see that the length of tunnel is one of the factor. Other factors are the ground. The ground was very different. So of course, using double shield machine, you get the utilization, which is better. But we have to consider the ground and this when you are doing a comparison, doing a comparison with a similar project is more where you can see more representative, where you can see that the utilization values are same or is different. So yes, for double shield machine, you get a higher utilization. But for these two projects, there was a bad geology and the tunnel length is also very high. And therefore you get this particular utilization value.
Okay, thanks, Dr. Khetwal, and thanks for the question. I don't know if we have more questions from the audience.
I have just a curiosity. Is the CSM procedure very highly time consuming or not?
Time consuming, you mean?
Yeah. In terms of time for the prediction, you need days, hour.
No, so what here I have done like 50 replications almost. So for me, it took like 2 hours to do all these replications. So it really depends on how if you have a reasonable PC, it doesn't take much longer. And also if you have all the data as was shown in this, like if you have all the data that you can put it in this data template, the simulation model will read and will give you results.
So the most of time maybe is related to collected data, so to organize your data set.
Yeah, so I think so these information are usually available for and is a part of, is not just specific for this utilization estimation, but as for the whole analysis, you need this data. And therefore it is, if you are working for a project, you get these data pretty simply. However, like if you want to do a comparison, that you cannot make a decision whether you want to use a muck transportation system as in train or in conveyor belt, then you can change these values here and you can see how the utilization values are changing. Yeah, for example, I would say that for the Nosooth project, one of the project, we tried and we saw that for the first 6 kilometers, if we changed from muck conveyance system from conveyor belt to train, it was not changing the utilization much. However, once we reached after 6 kilometers, the utilization increased for the conveyor belt, and the train was causing much of the delay. So then, as was done in the project, they used conveyor belt and which was the right decision. Yeah.
Okay, thank you very much.
No problem.
Well, thanks for your question, Federico. And well, I've also another curiosity, and this is well regarding tunnels excavated in very particular rock masses like those represented by CDGs or completely decomposed granites. What could be the performance of this methodology in such environments when sometimes you don't have much information, borehole information, or and you have to predict some parts of the rock mass from very small amount of data. How would be the performance of this methodology in such environments?
Yeah.
So maybe mention something.
Yeah. So here you can see that these were some of the ground troubleshooting measures that was considered. So if you have like a very bad ground, you could consider a combination of these, time activities, and that will significantly reduce the utilization value. As in the carriage project, in one of the papers, we have shown that the carriage project had the CZ crushed zone grounds, and it was where the utilization was very low, around 3%. So this you can see in here, and you can put it in these ground troubleshooting measures, and you can combine them, and that will show you the utilization value much lower than the average utilization in general ground, in competent ground. Yeah.
Well, thank you very much. I don't know if we have more questions or not. Well, in any way, we can proceed with the seminar closure if there are no more questions. So we are at the end of this 9th ISRM Young Member Seminar, and I would like first to acknowledge the participation of the speakers and the help of my colleague co-chairing this seminar, Dr. Federico Bagnon. And I'd like to thank also the ISRM for helping us on behalf of my colleagues with the organization of the event. Special thanks to Dr. Alessandro Valletta and Dr. Anuradha Khetwal for the very interesting and valuable presentations and works, which of course address two relevant topics in rock mechanics and rock engineering. And we do hope this seminar provides you, the little audience, with new insights and new challenges for future research. And it could be a periodic event for sharing ideas about rock mechanics and related topics. For this reason, we would like to invite you to the next seminar, which will be held by the end of October 2022. The time is to be confirmed, and the speakers will be Dr. John Justo Urrutia from SEMR, a company in Spain, with the topic of his talk is application of recent fracture mechanics criteria to notched rock fracture analysis, and Dr. Jonathan Overton with the topic differentiating cratering mechanisms in rock blasting based on geomechanical characterization. So further information about this event will be available on the ISRM newsletter and website. So please, if you are interested, keep in touch not to lose the next session of these webinars. And if you are interested in participating, or you know someone who might be interested in participating in our seminars, please contact us by the email shown on the screen. And I would like to thank you all for your participation and wish you a wonderful and safe day. So we can close this seminar. Thanks to everybody for being here.